Hey folks, Cool18 here, and welcome to Let's Try TIS-100. This is a new game by the people from Zachtronics. Those are the people who made Space Chem and Infinifactory. Basically, they're people who like to make you feel pretty stupid with their incredibly sophisticated puzzle games based on sciencey things and other type stuff. In this case, this is actually a programming puzzle game. The TIS-100 is a computer. It's the Tessellated Intelligence System, and requires you to do sort of assembly-style programming in a multi-node computer setup. I don't know. We're gonna look at it. I actually haven't played at all. All I've done is taken a look at the reference manual, which basically reads like an old computer module. It talks to you about the different types of instructions you can run, a couple of different types of nodes, that sort of thing. And that's it. So we're going to jump right into this, but I think it's going to have a bit of a sort of a murder mystery sort of feel. Even when you start up the game, it's cool because it just looks like a computer booting up. So it says, welcome to the TIS-100. Before you begin, we strongly suggest that you print the TIS-100 reference manual, an important part of the experience, and is essential to mastering the TIS-100 architecture. Well, I haven't printed it out, but I do have it up there. So, based on the interface here, it certainly looks like this is a series of puzzles. I suspect that the self-test diagnostic is a tutorial kind of thing. All right, create a new program for this. So let's create a new program for the self-test diagnosis. Self-test diagnosis. Read a value from in.x and write the value to out.x. Read a value from in.a and write the value to out.a. So in.x is over here. So we've got an input. So these are the nodes, and you can write programs in each one of these nodes wherever you want. And they're connected to their neighbors. You can see this node here is connected to this neighbor, and they can read and write in both directions, and here as well. Here we've got some broken nodes. So really this is going to be an isolated program over here. And yes, there is an input into our entire system over here, in.x, and there's an output at the bottom, out.x over there. So read a value from in.x, write the value to out.x. Looks like the program's already written for us. It's going to move the value from the upwards connection, which is here, and it's going to move it down. It's going to do that again, and it's going to do that again. So that should transfer over there. And then there's another bit to the diagnostic. Well, actually, let's run this now and see what it does. And there we go. We can see the values are going through there. That's perfectly fine. That's the first step, but the second step is just frozen because nothing is happening. So we're going to stop that, and basically we're going to have to write our own version of this. We have to get the data from in to out over here. That should be pretty straightforward. We're going to move from up to left. We're going to move from right to down. Move from up to down. I think I can use there's a key sequence I can use to switch nodes. I don't remember what it is. I'll have to double check the hotkeys, but I'm pretty sure there is one. We're going to move from up to right, and we're going to move from left to down. So now if we run that, everything will go at the same time and should complete. Yay! Well, there we go. We've got some comparison scores based on how efficiently we did it. Obviously, there's not much room for efficiency one way or another. It looks like it compares against your friends list, which is cool. All right, we'll return to the list of segments. Segment 10981, signal amplifier. Let's create a new. So what's the segment map? Specification editor. Create new specification. Is this like a mission? You can create your own missions. That's kind of cool. All right, our mission here is to read a value from in.a, double the value, and then write it to out.a. Pretty simple. So, excuse me, what we're going to do is, so double the value. Well, there's a couple ways I can think of doing this. So we have accumulators. We can all do it in the same box over here, and I guess we can do that. So what we can do is we can move up into our accumulator register, which is right over here. Then we can add the current value of the accumulator to the accumulator, right? If I just say add 1 to this, it'll add 1 to the accumulator all the time. But if I say add accumulator to that, that'll work. And then I can go move accumulator down, and then here it's move up, down. Oops. Thank you for giving me the error right away. That's very handy. Move up to right. Move left down. Now this will hang at first until it gets the command. Now, what I'm concerned with is this going to, well, let's try to run it and confirm that it is indeed functional. But it's taking 3 cycles here for each move. Yeah, I was going to say, you can probably do it in about half as many cycles. And you can see here, Terrible Plan has indeed done that. Now, this used fewer nodes. If we do add one more node, how could we get these to add together? While using fewer instructions. Because I can alternate. What I could do is send one value down, one value to the right. And then how do you combine them in less than 3 instructions? I don't see how you can. Because let's say I had a value here and here. Move up to the accumulator, add left, and then you still have to move the accumulator down. What if we execute it in parallel? And actually, instead of reading up, okay, this value here, all we're going to do is we're going to grab, all right, we're just going to bring it down because we don't want to use too many nodes. Move up to down, and this is going to run into 2 steps. It's going to move up to right on one tick, and then it's going to move up to down on the next tick. So this is going to move from left into the accumulator, add the accumulator to itself, move the accumulator down. Okay, we can do this. So this is going to do the same thing. It's going to grab from up into the accumulator, add the accumulator to itself, and then move it to the right. And then this is just going to go move, well, I guess I could have left what was there. Move up, down. So this is just going to shove it down here. It's going to alternate. It's going to move it to the right. This is going to run its execution. It's going to move it down. It's going to run its execution. This is going to read from up and from left. So we're going to do the doubling in parallel. There we go. 84 cycles, which is the same as what the other person on my friends list, Terrible Plan, got. Achievement unlocked. Parallelize. Excellent. Parallel execution there. I don't know if it triggered because of a specific number of cycles that were used or what. But this is going to be the whole theme. You're going to try to use as many nodes as possible to optimize execution. Okay, oops, no, I wanted to run fast. Return to the segment list. Next thing we've got here, differential converter. Read values from in.a and in.b. Write in.a minus in.b to out.p. Write in.b minus in.a to out.n. Okay. So we are differential converter. We're going to take the difference between the 2 nodes and output them at the bottom. Let's see here. Got a lot of extra nodes to play with. Huh. I mean, obviously we're going to start by moving up into something in both cases. Do you want to swap anything from side to side? Well, oh, this is interesting. All right, let's try to sort of brute force it first, and then try to see what we can elegantify later on. So let's say we move this side up into the accumulator, and then sort of do the same thing over here. But then we're going to grab what are we going to grab? If we write save, then what that will do is it will put the accumulator into the backup. Oh yeah, we've got labels and stuff like that for all kinds of commands as well. It's going to save it into the backup, right? If I run this, that's what's going to happen? Yes, it is. Okay. So we're going to put it into the backup. Then we're going to subtract from the right. So at this point, we've got A minus B, and then we can move accumulator down, move up, down, move up, down. So here, obviously, what we're doing is we're gonna move accumulator to the left, and then after we've moved the accumulator down, we're going to swap backup and accumulator, and we're going to move accumulator to the right, because you can't read from backup directly. And then we're going to wait. So this is going to move it to the left, do a little bit of processing. Then we're going to grab from the left. Actually, we're going to subtract left from our own accumulator, and then we're going to move the accumulator down. So this should technically work, but it's not very elegant. Yeah. 393 cycles. And you can see, terrible plan, this person here did it in half as many cycles. So rather than doing all this swappy-doppy stuff, we can use more nodes. What we'll do, what I could do is grab up into the accumulator and then move the accumulator to the left right away. No, I don't think we even need to use this bank. I think we can still just use these nodes going straight down. All right, we're going to save the input into the accumulator. Right away, we'll copy that downwards. And then we'll also send it to the right. And we're not going to send anything left here. If I do this, then they'll actually be in sync relatively nicely. All right, copy it to the right and then move it down. Well, actually, I guess it's not going to matter one way or another. Because what I was going to do over here is I'm going to copy B into the accumulator and then move the accumulator down. So the first number this is going to get from above is actually going to be the unsubtracted one. And its job is to move that one to the left. Move into the accumulator. We're going to subtract from the right. And then we're going to move the accumulator down. So we pass the raw value here down, and then the raw value to the right. This one here is going to move the raw value down, but it's going to grab the value, move the raw value down, subtract the other one, and then move the difference downwards. Here we move, this is going to be in the initial raw B that gets moved to the left here where we do the subtraction and then continue to move everything down. 238 cycles. Better. And we're using more nodes than Terrible Plan did as well. Crap! I don't like doing things worse. Oh, would that work? And oh, that percentage idleness, that's really handy too. Because they're spending a lot of time just waiting. I mean, I can shove things down faster and do more math over here, but I think that would be more cycle per node, so I don't actually think that's an improvement. You know what? We'll just come back to that one later on. Signal comparator. Let's do one more of these and then we'll end this video. I don't want to go and like break down all these puzzles right away for people. Plus, doing them right is going to take a little bit more time. Okay. So it's interesting. Debug. That's new. Compute node diagnostics microcode dump. Found a block of static memory. By the way, this whole thing is set up with a little bit of a, I don't know, mystery-ish kind of thing. This computer, I think, belonged to my Uncle Randy, and he has died. All right, this node. Found a block of static memory, but it's in a proprietary format I never saw before. Can't make heads or tails of it. Oh, brother, there's just too many different kinds of machines coming out now, and I like tinkering with them as much as the next guy, but when every Tom, Dick, and Mary implements their own memory address scheme, it's all... Okay, so this is actual text I'm finding in that node. I say the bottom's going to drop out of the microcomputer market. Soon. Mark my words. Okay. Read value from in. Write 1 to G if n is greater than 0. Write 1 to E if it's equal to 0. Write 1 to L if it's less than 0. When a 1 is not written to an output, write a 0 instead. Okay. So move up, down. I'm going to bring everything down to here, and then go to the right. And then what we can do... Oh, it's the other way around. You can write labels, and then you can have... It's... what's it called? Jump... What's the syntax for it? Jump equals 0, not equal 0. Jump greater than 0, less than 0. Okay, that's what we want here. So for G is if it's greater than 0. So if it's greater than 0, what? Oh, it uses the accumulator, right? Yes. So first we have to move left into the accumulator. And then actually continue to copy to the right. Accumulator to the right. If the accumulator is greater than 0. Actually, what does the jump syntax look like? Okay, like that. Oh, so we don't need a true or false. because the default is going to be to move the value of 0 down. But we overwrite it. We jump to true and move 1 to down if it's greater than 0. And then everything else does the same. This doesn't actually need to send anything to the right. E is if it's equal. So if it equals 0, and this one here is if it's less than 0. Whoa, errors. So -2, hold on. We got a -2. Is this the expected? This is the expected. We wrote a 1. How's that true? We move the left into our accumulator. Move the accumulator right. If it's greater than 0, go to true. Oh, it's because it falls through. Derp, derp, derp. It doesn't restart right away. We need another label here. Start. Jump. Start. There we go. Because otherwise it's falling through the next one. And we need labels. There we go. Now each one of these nodes have a lot of processing to do. But I can't really skip past them. I wonder if... Running random test. Hey, I use less cycles than Terrible Plan here. I wonder if there's another way to optimize it by doing some sort of pre-math. I'm not sure that there is. But there we go. This is TIS-100. Again, those were relatively simple examples there to get you started. Signal edge detector. Let's just load it up. Read a value from end. Compare value to previous value. Write 1 if changed by 10 or more. If not true, write 0 instead. The first output is always 0. Neat. That would be a lot of fun. How do I just pop out of here? There we go. Erase this program, return to the segment list. Repair 3 more, and then we get to unlock more nodes. And there should be more of those, there we go, more of this debug information here from time to time with some more background story about the, about the mystery that you want to try to figure out. Well, you're mostly just here to actually solve computer problems. So this is TIS-100. It is available on Steam, probably other places as well, and it's relatively inexpensive. Right now, I only see the Canadian dollars, but it's currently available for $7.01 Canadian on Steam. So it is a relatively inexpensive game. I think a great little puzzle game. You can stretch your brain, especially when it comes to all the parallel execution, right? Like my favorite one are the ones, there we can reload one of our programs, is starting to think in this sort of way where we're splitting the execution, breaking down the node into a couple of different behaviors and doing that. And these, again, are still simple little problems so far. But if I've learned anything from playing Space Chem and Infinifactory, is that, that's what it's called, right? Infinifactory? Is that these guys will come out with devious, horrible problems later on that will just wreck your brain and give you a headache. And that's awesome. See you next time, folks. Bye-bye.